I'm Tracy Defoe, and myself, Mark Rosenthal, and Maria Grzenka are three of the founders of Kata School Cascadia. Kata School Cascadia is one of the world's Kata schools. We are partnered up with the AME Western region to bring you this series on Kata coaching. It's a six-part series. The first one was What is Kata? And the second one was all about the challenge. And today we are grasping the current condition. I have to warn you, this is one of Mark Rosenthal's favorite topics. Over to you, Mark.
Okay, well, thank you, everybody. We're going to focus today on the step of grasping the current condition. And what we're trying to do is answer the question, where are we now? Quick recap for those of us from the previous episodes of the steps of the improvement kata that we're going through. We have a learner and we have a coach, and the learner is working to understand the direction and challenge, and then to grasp the current condition, establish a target condition with that current condition information, and then begin an iterative process of working experiments against the obstacles toward that target condition. Meanwhile, we have a coach, and the coach is there with the learner, not just giving assignments, not just, hey, come and tell me how it went when you're done. And the objective of the coaching is for the learner to internalize this thinking pattern, and ideally on everything they do, but certainly in the context of improvement. In the first session, Maria and I went through a coaching cycle, and that was really early on, and I want to go through it again, actually the improved version, and have Maria coach me again through the same problem with the same dates, just so that we've got some context for what we're going to do today. So with that, I'm going to ask Maria to be my coach.
Okay. Are you ready, Mark?
I am.
All right. Hello. What is your challenge?
My challenge is that we need to get to where we're producing 700 faucets consistently every day without any overtime, so we get it all done in the shift, so that honestly we can end up getting our evenings and weekends back.
Cool. What is your target condition?
So my target condition in 2 weeks is that I need to get Alice's, the first operator, Alice's lowest repeatable time, so that it doesn't exceed the 40-second takt time. I think if we can do that, I can get to at least 600 faucets a day consistently before we start kicking into overtime. And I don't see right now any fundamental changes in the operating pattern in order to get that to work.
Okay. What is your actual condition now?
So the actual condition now is against the challenge of 700, and then the current requirement of 650, and you can see that we are on a daily basis, we're flirting with 600 and not even making that consistently. If I start looking at the process, the actual steps of the process, we've got 4 people. We've got Alice, we've got Betty, Chuck, and Debbie all working on the assembly line, and it's actually a pretty smooth flow. I just think there's a lot of issues with work balance and interruptions. So you can see on the load chart here that the reason I'm going after Alice's lowest repeatable time is that her lowest repeatable time is right now even exceeding the takt time for 650 a day. So we're not even going to make 650 until we deal with that. Mm-hmm. Plus, you can see there's variation that cascades down the line. If I look at Alice's work cycle specifically, you can see that each cycle pretty much flirts along that line of just above 40, but there's also interruptions and variation involved. I'm working right now just to drop the floor there so that we can at least start to get some consistency and see what the impact of the variation is.
Okay, what did you plan as your last step?
My last step formally was to just do some math on those lowest repeatable times in order to see, if 4 people are even possible to get this done.
And what did you expect?
So I predicted that 4 people were going to be enough to get to 650 if we can address the wait times and the variation.
And what actually happened?
Well, math gave me a 3.9. So, yep, 4 people, we should be making 650 with 4 people.
And what did you learn?
So I learned that we're going to need to ultimately find some cycle time savings throughout the line if we're going to get to 700. And then I also use this information to establish my target condition of addressing Alice's time first.
So what obstacles do you think are preventing you from reaching your target condition?
So there's a couple right now that are obvious. One is Alice's cycle includes 3 or 4 seconds of return walking time. And the other one is I don't know what other timing details are affecting Alice's cycle.
Which one are you addressing now?
So I need to get more information. So I'm going to address the I don't know enough of the details for Alice's cycle time.
And what is your next step?
So my next step is to get back out on the line and do a detailed time study of Alice's work.
And what do you expect?
I expect to learn where the time goes, and just to put it in the most simple terms, what are the sources of delay? Where's the time going? Where's the wasted motion here?
And how quickly can we go and see what you have learned from taking that step?
Actually, I expect to be able to do this in a couple of hours, so we can talk about this tomorrow.
Great. Thanks, Mark.
Okay, with that as a baseline, let's look at where we are. Let's orient. Those 5 coaching questions happen here. So a target condition's been established, and now we've got obstacles, and this is where we get the coach into the cadence of those 5 questions. In our last episode, we covered understanding direction or challenge, and that shows up on the storyboard here up in the corner where we write down the challenge and we establish that. Today, we are talking about this step of grasping the current condition, which is what shows up on the storyboard in the center part. And there's a lot here, and what I plan to do is just go through each of these artifacts a little bit quickly about how they're made, but really the context is what information is the learner gaining by actually doing this work. There's some key questions we want to coach our learner to finding the answers to. How are we doing against the challenge? And that's establishing that outcome metric, which Tracy talked about last time. Where are we versus the goal? What does the customer need? When do they need it? What's the definition of on time and defect free, if that's relevant? How are things operating now? What's the normal pattern of work? What are the actual process steps that people are carrying out today? And what is the actual rate and timing of the cycles of output at each step of the way? Do we even have capacity? If I do some math, how many people would be required for success if our process were stable? And do I have machine constraints? And then really, what does all this mean? Why does the process perform as it does? And the coach's objective is for the learner to be able to really answer questions or questions like these and point to facts and data to answer them, not just speculation. So I'm going to start really quickly with the first because Tracy kind of linked to this last time. If I look at the storyboard, as I'm taking that challenge and I'm just pulling it down, I'm saying, what do I need to measure to tell me if I'm meeting the challenge? In this case, it's really easy and really obvious. Sometimes it involves some discussion. I have an outcome metric of how many faucets I'm producing during the regular shift, and I'm either hitting it or I'm not. And I can see my trending on this run chart. So I want to set up that run chart and start measuring right away. How am I doing against the challenge? So that's what my first thing I want to ask my learner to do. And honestly, if there's back history like daily output, let's go some back and let's just get that going before we do anything else. Even as we're working to grasp the current condition, let's start measuring the outcome and start tracking and trending it. That's the easy bit. Okay. So next question I'm going to ask is, what's the definition of on time? I'm going to kind of leave defect free kind of as a given right now, except that if I end up producing a defect, it doesn't count as on time. So let's talk about that, because this people can get their head wrapped around this. In traditional manufacturing, what we're really talking about here is takt time. And I'm going to go through takt time, but there's a lot of different contexts that we can go a deep dive into at any time. What I want to do is I have an actual rate of output, which is what was on that run chart for the operator. We're going to go through measuring this later, but right now just the measurement has no meaning because I have to ask compared to what. So what I want my learner to do is understand the required rate of output, so there's a point of comparison. Here are the lap times essentially that we're making for the rate of output of the process, but what's the standard? What are we trying to achieve? And if I go back to the run chart of the first operator, the actual rate of output, right, is all of these dots and the lines. That's the lap times essentially for the first operator, whereas the required rate of output is defined by the takt time, and we'll get to this planned cycle time line in a little bit. It's just math in this case. I've got a one shift operation, it's 8 hours, that gives me 480 minutes, but I've got breaks, I've got a meeting, I've got some cleanup, I've got 435 minutes to actually make stuff during the course of the day. That's 26,100 seconds. Okay. Right now, even before we hit the challenge, we need to get 650 units out every day. So pretty simple math. If I take how much time I have got to get 650 units out and I divide that by 650, we need to be finishing a faucet every 40 seconds to be successful. In the simplest form, that's what takt time is. But this kind of creates a question, and I'm just going to ask the group, put it in the chat, speak up, okay? If I were to plan my line to just be able to meet that 40-second cadence, what would happen as I tried to run? Any thoughts? Yeah, I wouldn't make it, okay? Stuff would happen, okay? Any hiccup, it's going to put me back into that overtime. Yeah, okay. Yes, this is what would happen if I planned to run 40 seconds per faucet. Fail, yeah, okay, all of that stuff. Here's what I want to do is I want to put a little time in my back pocket. So what we want to do is we have this thing called planned cycle time. That's Kata jargon. I think some folks at Toyota call this operational takt versus customer takt. Whatever that is, whatever you want to call it, I don't care. But this is the speed we are actually going to plan to run the line at. And it's going to be a bit faster than that customer takt. So we have got some time to put in our back pocket. A good rule of thumb to start with is to just derate and take 85% of the takt time and use that as your planned cycle time. You can do fancy math on it, but let's just start with this as a goal. And then as you learn more, maybe you can run the line a little tighter as you get some stability. So the way I like to think of this is that takt time, that 40 seconds, that's the customer requirement, but we've got a process requirement that we're going to try to hit, which is at 34 seconds in this example. So what that means is if the process cycles are longer than 40 seconds, we're falling behind. So I want to design the work so that if we have a problem-free cycle, it's going to hit 34 seconds in this case. And what that does for me is every time I'm successful at 34 seconds, I get to put 6 seconds in my back pocket and I can save up a little bit of time. And if I do have a disruption, after 10 cycles, I've got a minute and I can start to absorb some of those delays and unforeseen things, still be successful at the end of the day, but have a little bit of headroom that we can use to respond to issues for line stops and all the rest of that. That's the whole idea here. Looking at that cycle time run chart, which we're going to prepare next, is there's where we express that 40-second takt time, and here's where we show the planned cycle time. So right away, you can see that I would love it if those blue dots and lines kind of kind of bounce back and forth between that dotted line and that solid line. That would be ideal. Okay, now that was takt time. That's a classic industrial example, but in all cases, I want to establish some kind of reference standard that tells us what should be happening with respect to timing. And it can take a lot of forms. This is just the classic, and we're going to stick with that right now just because in the interest of time. Now we've got some parameters. The next question is, what's actually going on the line? We got two pieces to this. The first one is, what are the actual process steps that are happening now? Our standard fallback here is a block diagram, a couple of examples of a block diagram, and then I'm going to show you how to make one. This one is from a catering operation in a regional hospital in the Southeast. We've got here the high-level task steps. We've got the work breakdown, who does what, and so that's the division of labor. And another example, this is from a small company, accounts payable, and in this case, they are already working on stuff, so they've already modified and they're keeping up with their current condition. And by the way, you can kind of see those run charts and those takt times down here, even for accounts payable. So you can start to see some of the artifacts here. The first step in building that block diagram is just to identify what those primary work steps are. You've got to go to the actual process. You have to actually watch it. And you can't do this from memory. You can try. Hey, this is another technique. Write down what you think happens, and let's use that as a hypothesis. And then we can look what actually happens and see how right we are. At this point, we just want to focus on the high-level steps. We'll add detail later if we need to. I just want to get a basic understanding. So typically that task would be a verb and an object, enter customer info, install Marzl veins, send invoice, one task that has a done to it. So just as a demonstration, just going to go through, make a faucet on the line. I'm going to run this at 3x speed. It takes about 2 minutes. It's going to take 30 seconds here, just so you can get a feel for the kinds of things we want to write on the block diagram. So let's just follow a faucet around. And this first operator is Alice. She's the one that I've been focusing my attention on. Again, this is 3 times speed, just so that we don't end up watching this for 2 minutes. We would slow it down if it was actually training, right, and practicing doing this. So there's the faucet she just finished. And it gets boxed, it gets checked, and put in a case. So that's the whole process, obviously really quick. And it normally takes a little bit of time to get down there and really understand. But now I've got a list of the tasks that I think are going on here. So I just want to build literally a block diagram, which means let's put those tasks in blocks. And now there's the fundamental. So let's add some more information. Are there any automated steps? In this case, there aren't any automated steps, but if I have an automated task, that's something that can run unattended. Maybe I load a machine with a unit, get it going, and then the operator moves on and does something else while that machine is running unattended. That's what we mean by automated step. In this case, they're all manual, but if you have them, just indicate that across the dot. CNC machining step, I load the machine, I start it, and then I start processing the unit that just came out. Just make a note that this is running without a person. Now, next question, how does the labor divide? In this case, it's pretty obvious. Again, this is a pretty simple example. And so what are the work zones of each individual team member? And this is going from left to right. Sometimes it's a little confusing because the line goes from right to left in the video. Okay, then where's WIP accumulating? And we saw a little bit of it in the video, right between the first and second operator. Sometimes we end up with 2 faucets there. Sometimes we end up with 1. Sometimes we don't have any. In your case, you may have dozens or hundreds of units of WIP between processes. That's cool. Just make a note of it. We use a little warning triangle up there. Okay, in this case, the WIP varies between 0 and 2 pieces. Now, what else is going on that's not part of the process? Characteristics that may materially affect the work. So occasionally I see some rework. Anybody will tell you there's lots of walking. I turn the sound down. But there's a pretty loud environment in there. And also we have in the last operation, there's parallel work going on because Debbie's building up boxes while she's waiting for the next faucet. So all of this of noting what's going on, that's ongoing. As you continue to update. And you'll see lots more once you start timing cycles because you'll end up spending more time down there. Okay, so the last piece here is if I wanted to look from the customer's perspective of what are they seeing as a cadence of output, where do I want to time that? In this case, it's really simple. It is at the end of the line. When a faucet goes in the box, boom, that's the next faucet. Sometime after that, there's the next one. That's going to tell us if we're making takt time. As you're going, you want to update it. This is going to change, especially as you're rolling through target conditions. If you're changing the process, keep this up to date so that it always reflects the actual condition now, rather than, hey, here's what we did when we started this.
I just wanted to jump in to kind of pull us back for a minute. In the coaching cycle that we did in the introduction, there was a lot of information that Mark shared in response to the question, what is your actual condition now? So he's showing you all these things to gather information about the current condition. Typically, this takes a bit of time to gather all of this information. So although we're showing it to you in this condensed version today, keep in mind that this might take like multiple coaching cycles over multiple days, or even like a big block of time in a half day or something to gather all of this data. Because what we're really trying to do as a coach is teach our teams, teach our learners how to analyze and understand the process that they're working with.
On a line like this one, it would take somebody who knew how to do this a couple of hours. But each step could be an entire coaching cycle, asking, okay, what's the next thing you need to learn? What's your step to learn that? And just rolling through each of these steps as we go. So a little bit every day is a good way to break it down rather than trying to pull your line supervisor away from supervision, for 4 or 5 hours during the course of a workday. So this can be progressive, and that's a really good point. So we've got the actual process steps, but now, okay, what's the actual rate and the timing of output? And here's where we're going to build those run charts. We start with the exit cycles that reflect what the customer sees, but we also want to then get the timings of every major block of work. In this case, the last operator cycle and the exit cycles for the cell are the same thing, so we don't have to do that separately, but there will be cases where something other than a person's work is pacing the end of the line, in which case you may end up having to do that twice. Here's what we're interested in timing, is I'm looking at the time interval from the time one unit comes off until the next unit comes off, until the next unit comes off the line. That's what an exit cycle is. And of course, we can have exit cycles for individual operators as well, which is what those other charts are going to be doing. We're not right now looking at the flow time through the whole line. And the reason I'm going through this is people have different definitions for what they mean when they say the words cycle time. And they're all right. It's just to be clear amongst you when you say those words, what do you mean in this conversation? And what we're looking at in this conversation is the cycle versus the takt. Not necessarily operator task time, although in this case, it's all operator task time. But again, if I've got machines in the middle, I want to look at exit cycles from the perspective of the product moving to the next operation. Ideally, if you've got time, 20 or 30 cycles is great, because if the law of large numbers. After about 30 observations, if nothing changes, whatever you've seen, you're likely just to see more of it. In this case, you want to find a place, if you're trying to time laps in a foot race, wherever you stand on the track doesn't matter, right? You're just clicking your lap timer every time something, the person or the car goes by that point. So you do want to pick some kind of observation point where you can clearly say, okay, that one's done, next one's done. For an exit cycle, if it's at the end, that's ideal because it just helps wrap your head around it. We're going to use the product in the carton for this example and just let that stopwatch run until that cycle returns no matter what. And I'm going to show you an example of this in a bit. If there's wait time, if the person is waiting consistently, you want to make notes of that because that's important, because if they're waiting every time or nearly every time, when we look at total work content, we want to pull that out, and we'll show that in a second. And if you see a lot of out of cycle work, driving variation, hey, make some notes of that. This is really effective if you've got a couple of people doing this, one taking notes and the other just grabbing the times. Here's an example. I'm just going to go through about 6 or 7 cycles. Again, I'll speed it up when it's relevant, but it's going to slow down in the middle to show you another good one. Okay, so let's just watch. Okay, so number 0, right? She's halfway through the cycle. Boom, that's where I start my stopwatch. That was number 0. So now we're timing the first one. A little bit of waiting there. Okay, weigh it, put it in the box, 30 seconds. Now we're just going to speed up for a couple more just so you can get an idea of the cadence. And you can see on the lower right here, what we're doing is we're making notes, right? Now, slowed back down to real time because I'm going to keep that stopwatch running on this one because she's doing other stuff. Huh, this is really interesting. So what's going on? Well, I make some notes here. Okay, she had to build up a carton and she disappeared back in the back. You can see her under the timer. Okay. She's doing something back there. Okay, what she's doing is she's schlepping 3 cartons off of the conveyor onto a pallet, and then she picks up her regular work cycle, but that added another 40 seconds or so. So this is just the process that we want our learner to learn in order to see what's actually going on. The next couple are pretty nominal, but you can see that there's some small amounts of variation, but it's pretty consistent, right? When she gets in a rhythm and nothing's interrupting her. So we just want to continue this process of getting these times and watching in order to understand what's going on. Okay, so the next one was 27, next one's 30. There was a little bit of wait time. And if I continue, I'm just going to keep getting cycles. By the way, this whole this whole process in this case takes about 20 minutes, just to give you some perspective. And I got 36 of them, I think. And you can see there's a lot of weight starts to come into the play. Now, I want to take those times and I want to build up a run chart. And I can now really start to build a picture of what's going on right away. Holy moly, there's a lot of stuff happening here. Now, how does that compare? Well, there's my takt time is 40 seconds. There's my planned cycle time. And we're starting to get a picture out here of what's going on. The next thing that I want to know is if we had a stable process, right? if there was basic stability, what would the work cycle be if there weren't for all this variation? And the easiest way I've ever been taught to do this is just take a ruler, and when you start bumping into dots, that's probably a good spot. I would expect different people to vary. Some learners will be plus or minus a second or two on this. I'm not that concerned about it. We're just trying to get an understanding. But in this case, I'm going to say my lowest repeatable time is 30 seconds for this operator. The next question is, what's the range of variation? And I want to build that on the chart. So let's take the lowest point, and let's take the highest point, and let's just build a bar between them. So right now, this is right out of the book, but maybe I want to add some notes. So now I can see some of the sources of variation that I was able to capture. And this is just making this richer so that my learner, if they have all of this stuff on here, they can more easily explain it to me or explain it to someone else, which means they understand it better. Maybe there's a consistent wait time. So what would those cycles have been, right, if we didn't have the wait time? So, if that's relevant, I want to add those. Does that materially affect the lowest repeatable time? In this case, not really. Okay, so now I want to build those same run charts for all of the operators. So here's operator 1. This is the second operator. This is the third operator. In this case, if I took lowest repeatable time just based on the blue dots, when I take that wait time out, there is a material difference. So I use that as the lowest repeatable time here. And there's the one we just did. So
Hey,
I can
Mark.
start to see a pattern developing. And
I just kind of want to pause here. Okay, so we've got a lot of stuff here. And we started out with that outcome run chart or the output run chart against the challenge. And then we went out and watched the process and built the block diagram with all the extra notations on it, division of labor, where we're going to get the exit cycles. And then each of these 4 graphs is looking at the exit cycle and the lowest repeatable time and the variation for each of the 4 operators. So we're working with our learners to be able to analyze their processes in these ways so that you can get to the target condition of, I need to focus on operator 1 first.
yes.
Awesome.
Okay. So
Okay.
Paul asked if I'm doing multiple shifts. Yeah, especially if you're seeing different outcomes on the different shifts, which is very frequently the case. I'm not going to understand why I'm having those different outcomes unless I go and I look at what's going on each of them. By the way, here's a real world example that came from our Kata Together event in Chilliwack a couple of weeks ago. And this was interesting because this was a line I think had an 8-minute takt time, and the total work cycles was about 8.5 minutes, and we're going to get to why that's relevant in just a second. Okay, next is, do I have capacity? So one of the things I like to do is take those bars that are at the end of each of the cycle charts and put them on one chart, which I call a load chart, which kind of gives us a summary of what's going on. I've got my lowest repeatable times. I've got my total variation. I've got my takt. Now here's my question. If I were to add up those lowest repeatable times for each operator, I got 42, I've got 36, I've got 24, I've got 30. That kind of gives me the work content to build a faucet. Here's kind of the question. If it takes 133 seconds to build a faucet, and I have to finish a faucet every 34 seconds, how many people do I need to be building faucets? Anybody got a guess as to how to calculate that really quickly? Yeah, okay. Yep, exactly. Perfect. Okay. If I were to take the sum of the lowest repeatable times and divide those by that planned cycle time, I, in this case, get that I need 3.9 people if I had a stable process. So the general model here is, if I ask how long does it take, and I divide that by how long have I got, the required rate. That tells me how many parallel operations I need. For example, it takes 5 minutes to put a car through my car wash. I want to finish washing a car every minute. I need 5 cars in the car wash at any given time. That's straightforward math, which works for the capacity calculation across pretty much anything you do. Machines, we think the same way, but if I have machines that are working in line with people's cycles as a respect for people thing, I don't want people waiting on machines. So if I look at what a machine cycle is, there's 2 components. If you think of your automatic dishwasher, you've got it loaded, you press start. It's going to run unattended for some period of time, and then it's done. And your next step would be to unload it and then load it again and then start it again. Those 2 things combined, the automatic cycle and the manual unload load cycle, give us a machine cycle time. There's my takt time in our example. There's my planned cycle time. Where I want to try to get to is where that machine cycle time, ideally, I'm going to derate a little more and make it strive to have it maybe at 90% of that planned cycle time. Now, here's another example. In this case, my automatic cycle is the same, but the unload load time pushes us high. So that's too long, but because that's manual work, maybe that becomes a target condition, and at the working level, we can do improvements, we can Kaizen that in order to get that down under where we need it. But if I have a case here where the automatic cycle pushes above the takt time, I'm into capital investments, I'm into engineering. The supervisor can't do anything about that. And so all this step is a sanity check to make sure that if we're asking somebody at the working level to improve the line, that they can actually meet the goal. In this second case, they can't. There's nothing they can do to get more out because that machine is pacing their work. Just think of a machine as an additional worker on the line, and everything else pretty much applies the same way. Okay, finally, what does this mean? Why does the process perform as it does? You know, maybe a good coaching question for this point, or really at any point along here, right, is what is this information telling you about the process? And that's just another form of what have you learned, but it maybe is a little more direct because, again, we are taking our learner through this in stages, in steps, and in each step, a little more information is coming out until it all gets together. So finally, why are we doing this? We want to understand what the customer actually needs. We want to understand how well we're meeting that need. We want to understand the normal patterns of work in order to understand why the process performs as it does, so that we can get enough understanding to establish a target condition. We are not looking for improvement ideas right now. It is what it is. It is a completely neutral, non-judgmental process. I'm not looking for waste. I'm just trying to understand what's happening. Once we establish a target condition and once we start to work toward it, we are going to see the things we need to work on in order to get there. That's part of why we just want to understand how the process performs as it does. So in our next episode, right, is how do we take all of this information and turn it into a target condition? So that's where we're going to go at the next session. So this is what the storyboard might look like at the end of all of this. This is an experimenting record of the steps of getting through this analysis, and I don't have a target condition yet. My next step at this point is to establish that target condition based on this information. Does the employee know you are observing and taking time? You absolutely want to tell them and make sure they're cool with it. I've in some cases have taught them to take their own times. That helped to diffuse a lot of it. You have to be respectful first. Is there a program that does this? Graphing process variation. Ink makes you think is one of the things I'm fond of saying quite a bit. I would much rather have people not use software to do this. I would like people to actually draw the dots because that way they're getting the answers for themselves rather than just looking at what a computer does.
Hey, Mark, there's a
Yeah,
question from earlier, and I think it was about your 85% buffer. And the
yeah,
question is, what is the basis for coming up with relevant buffer to put in? What considerations need to be addressed?
that's a guideline, right? But the consideration at the end of the day is how much buffer do we need to make sure that the variation that we're experiencing today does not cause us to be unsuccessful at the end of the day. And maybe we're going to have to get there. Certainly this faucet line isn't being successful at the end of the day. So I'm starting with that 85% literally just as a place to start until I learn more. You can go into some pretty heavy math if you want to around amortizing your changeovers and working all of that into your actual planned cycle time as well. And if you have that information, then use it. That's a somewhat more sophisticated approach, but for a beginning learner, let's just start with this and then see where it takes us.
So, Mark, there's another question in here around
Yeah.
OEE. So, in case
Oh,
the machine you suggested to consider a 10% less than PCT, is this a suggestion that we have an expectation of 90% OEE of that machine?
no. OEE is an interesting one. You got to be really careful on context because at the end of the day, OEE is the machine available when I need it. It isn't about is it running all the time. So you got to make sure that you're looking at it through that context, because otherwise you end up trying to run the machine faster than you need to. And here's my classic case of that utilization. You know, if you have a washer and dryer in your home, a washer cycles in about 25 minutes, a dryer cycles in about 40. If I were to go maximum utilization on the washer, I'd end up with a big pile of wet laundry. Yeah, so the utilization metrics are really dangerous. The question is, how fast must I go? Which really is how slow can I go? And in most cases, our machines are capable of outrunning what we need. Did that help?
Hey Mark, I got another question in the
Yeah.
chat around this run chart approach, not calling out common causes versus special causes. And therefore, it's not revealing if the process is in control or stable. How do you decide or prioritize which variants to review from looking at these charts before establishing a target condition?
Good question. Maybe we can go into that some depth next time as well. But I'm not looking right now from a statistical control standpoint. What I'm looking at is what's my requirement, because I have to meet the requirement at the end of the day. When I look at the steps that have to be done every time, there's my lowest repeatable time. Anything that knocks me out of that is variation, and it's likely going to be special cause variation because there's an identifiable cause to it. Even against my lowest repeatable time, I'm going to have small amounts of variation just because there always is. There's my common cause stuff, and how tight do you want it to go? So let's not worry a whole lot about it until we have to. When we're looking at statistical control, we're typically looking more at product characteristics than process characteristics as well. Let's get the process stable, and then we've got something to look at when we're looking at the places where SPC is appropriate.
That might have
Yep.
brought up a couple other questions because there's a couple more that came in. One from Paul. Instead of focus on station one, why wouldn't we focus on the whip and the variations first?
Station one is throttling my line. This is the load chart, right? Which is made from aggregating the run charts. If I'm looking at the first operator, okay, right now, her lowest repeatable time is above what I need to even be successful at 650. So she's throttling the whole line against my challenge of getting to 700. I'm addressing that first because I'm predicting that if I can get to the point where she's not throttling the line, it's going to change the dynamics downline on pretty much everything. We'll probably reduce a lot of that variation because there's a whole ton of weighting in there and make the issues more visible when her pace stops hiding the problems. That was my rationale for starting there, but we'll go into that next week in some detail.
If I could just add to that, I think that's
Yeah.
a really great example of how the challenge guides the activities that we do, right? I mean,
Yeah.
you
Mhm.
could go after a lot of wastes and a lot of activities in this line, but which ones are getting you closer to your challenge? And that's, I think, is where the focus comes from. It's actually quite liberating to know that you may not have to get detailed examination of absolutely everything in order to move forward towards your challenge.
There's two more open questions in the chat from Scott.
Okay.
If I have a team like my customer service group that has various activities / processes they are managing throughout the day, would you first just need to segment these tasks before utilizing the run charts?
Yeah, so that's what the block diagram does. That's really establishing what those steps are and at what point does that product move from one person to the next, and those are the exit points.
Okay, one more from Sandro. For lowest repeatable time, is it enough if it just happens 2 times, or is more better? Is more
Yeah,
worse
it's a
better?
bit of a judgment. What I'm looking at is if I were to take the obvious sources of variation out of the process, what would I see as a more consistent, stable rate of output?
Like what
And there's
could
a
be
judgment
possible?
call involved there.
Okay, I think we got all the questions from the chat.
Don't forget that we invite people to join us every Friday for a live Zoom about Kata coaching. You can find that link by emailing at info@kataschoolcascadia.org or find us on LinkedIn. That's the easy way to do that. I always say also, if you like us on Zoom, you'll love us in person. And so Mark's invitation to join us in person in July is also open and out there. Thank you. Thanks, Mark.
Thank you all for joining us.